Yes, hello, please, can you hear me?
Yes, Doc.
I was still waiting if the number could increase, but then it's still at the same eight. I don't know if we should wait or we should go ahead.
Yes, Doc.
So can I start or I should still wait for some to join?
Please, I think we can start. Then, as and when they join, they will join us.
Yes, because the last time I think it was Friday, right? When I said that
Yes.
we are meeting on Wednesday, so I was surprised that nobody joined the link. I don't know if you forgot that we have a class. We have booked for Wednesdays and Fridays. So that's okay. Let's try to do something. And I don't have much time. And so, well, we are still talking about our electrochemistry. So the last time we tried to consider the various types of cell, which is the galvanic cell and the various types that we have. But today we want to look at how we generate our electrons. That is electrolysis. Electrolysis basically, please, can you hear me?
Yes, Doc.
Okay.
Loud and clear.
Yes, Doc, we can hear you clear.
Okay, that's okay. So electrolysis basically is just where we are just generating electrons, and that of course this generation of electrons are coming from this chemical interaction, and this chemical interaction basically will be from a molecule, and that in that molecule there's just going to be bond breakages, and of course out of that bond breakages we have electrons being released, and mostly the reactions that leads to that release is just of course, something must initiate that. That's the redox reaction. So electrolysis just is just a method of separating these bonds, which from this element, which has formed compounds or molecules, and by separating the bonds, we are releasing electrons into its surrounding, and of course, these electrons generate this electric current, and so this is what we call the electrolysis. Well, in terms of cell, what happens is that in the electrolytic cell, we'll see that we are just going to rather use these electrons, or when the current kind of go through, then this current or these electrons initiate a chemical reaction. So basically, that's just a non-spontaneous reaction. But then in the galvanic cell, we're going to see that that's a spontaneous reaction where we are rather going to use the electrons to rather create these more or less like the electrochemical cell. So we are using these chemical reactions to really produce this electron. Whilst on the other side, on the electrolytic, we are rather using the electrons to generate or to initiate a chemical process. Now, if you take the electrochemical cell, of course, we have two ends, the cathode and then the anode. Just as we mentioned in the galvanic or the voltaic cell, we're going to see that the cathode is where the reduction is happening, and then the anode is where the oxidation is happening. Well, when we flip it, the electrolytic cell, the anode is where the reduction is happening, whilst the cathode is where the oxidation happens. So at the point, sometimes we miss the whole thing. So in the electrolytic, the anode is where the reduction is happening. I repeat that. The different cell or the different types of these electrochemical cell, which is the galvanic, so-called the voltaic, and then the electrolytic cell. In the galvanic or the voltaic cell, which has, of course, the two terminals or the two electrode, which is the anode and the cathode. In the voltaic or the galvanic cell, the reduction happens at the cathode side, and then the oxidation happens at the anode side. But when we come to the electrolytic, then that's the anode. So it's just a reverse. The anode is where the reduction is going to be happening, whilst the cathode is where the oxidation is happening. So in other words, the anode for the electrolytic becomes positive, and that of the cathode is negative. So please, let's push that way. But then you look at electrolysis, then we are talking about the electrolytic cell. So basically, we need to generate the electrons. And then these electrons are going to be initiating a chemical reaction, unlike the galvanic or the voltaic, where the chemical reactions will rather release the electron. Now, in the electrolytic kind of cell, we need to have electrons which are going to be initiating these chemical reaction. Now, the question will be, so where do we get to have these electrons coming from? Well, the process of getting these electrons to initiate this chemical reaction is what we call the electrolysis. Now, in every kind of a reaction, we need to understand what we call the activity series. Now, this is just a list of elements that goes through or are being ranked based on their reactivities when it comes to reaction. And so the reactivity series here is just a list of elements that are ranked according to the ability that they display. In every reaction, for a bond to be broken, what it means is that one element will have to display or replace, in other words, substitute another kind of element. So if you look at types of reactions, we can talk of the synthesis, we can talk of decomposition. So synthesis is also known as combination reaction. We can talk of decomposition, what we call the decombination reaction. We can talk of redox reaction, which is the reduction oxidation reaction. We can talk of this substitution reaction. The substitution reaction group into two. We have the single substitution and the double substitution. The double substitution is also known as the metathesis. That's the exchange reaction. So one element replaces the other, and the replacement is possible because some elements are much reactive than the other. So, for example, if I have, say, sodium, and then so sodium chloride, and then say I am in water. Now, what happens is that if you look at the activity series, you're going to see that. So I don't know if you can see my pointer. Let me just use that. Okay. So if you look at the activity series, look at where hydrogen is. Okay. And then, of course, when we go higher, look at where sodium is. So basically what it means is that sodium is much reactive than hydrogen. And so in a reaction where we have sodium binding to, say, chlorine, and then hydrogen binding to hydroxide, it's so easy for that sodium to displace the hydrogen in the hydrogen hydroxide, that is water, so that it becomes sodium hydroxide. So the activity series just gives us an idea how some element can easily display another. But for example, when I take, say, a compound of sodium, which is already a compound, and I put it in, say, a compound of silver, there will be no reaction, in the sense that silver is less reactive than hydrogen. So silver cannot display hydrogen. But then the otherwise, if I have a compound of silver and I put it in hydrogen, then hydrogen can display silver because hydrogen is reactive than silver. Please, is that okay?
Yes, Doc.
Okay. Please. Okay. So that is what the reactivity series, and of course, this displacement is what really initiates that. So what I'm showing here basically is that the higher the element in terms of its activity series, the more easily it can lose electron. That is just a meaning of it. Of course, reactivity has to do with electron interactions, or the easy to for that electron to interact with its environment. That makes the species reactive. So if you look at it, what it means is that when we take lithium and say calcium, the tendency for lithium to release electron is so easy than the tendency for calcium to release electron. In any case, calcium will have to release 2 electrons before it can be stable, and whilst lithium can just release 1. So it means that lithium will be much easily oxidized than that of calcium. That is what the inference is all about. So in electrolysis, what happens is that this series that we are seeing, it helps us to really protect which substance will undergo, or predict which substance will undergo oxidation and which substance will undergo reduction. So when you pick any of them as an electrode, so for example, if I pick potassium as an electrode and I come to pick, say, gold as an electrode,
Hello,
clearly
Doc.
it will tell me yes,
Hello, Doc. So
yes.
can we link this one to, let's say, the periodic table, whereby the elements are grouped according to the how it is, like the alkali earth metal and alkali metals and the rest, because the group one, the group two, you know that the group one element always loses electron higher than that of what the group two, although they are all reactive metal which loses electron, but as for the group one element, they loses electron higher, like the lithium that you are saying, it has an oxidation number of 1, which makes it more active to lose electron than the calcium, which has an oxidation number of number 2. Can we link it to that?
Yeah, and that's what we call the periodic trends. So
Periodic
basically,
table.
we'll be talking about the other trends like ionization energy, and of course those electron affinities and those kind. So that's what you are trying to refer to, and it all put together gives us a clear picture of how the element is going to be reactive or not. Because if the species has a kind of tendency of releasing electrons so easily than the other one, then of course that species. So if you take the periodic table, clearly, just as I mentioned, you can get to have the reactivity trend also in the periodic table. Is that okay?
Yes, yes, Doc.
However, in the activity series, we don't consider all the elements on the periodic table, but then we consider number one, the common ones that we use. Number two, the non-radioactive elements. That's what we consider, because if you take group one, if I pass lithium, I pass say potassium, well, sodium, potassium, then I'm going down there. You're going to see that I'm going to be hitting the bigger ones, which are radioactive in nature. So that's, we cannot clearly say that that is the trend on a periodic table, but we can just do a selection of these metal and then group them. And that we have done that, and this is a conclusion from the series, the reactivity series. Some call it reactivity series, some call it the activity series. Am I making sense?
Yes, Doc.
Okay. So I was just trying to come out with the electrolysis reaction, how we can generate our electrons to really initiate a chemical reaction. So basically, I'm just using the activity series to just, so the activity series just helps us to predict, okay, if I should take, say, potassium and then gold, then clearly it will tell me that the potassium is where the oxidation is going to happen, whilst the gold is where the reduction is going to happen. That's one way of predicting whether the cathode should be at this particular one, or this electrode should be the cathode and this electrode should be the anode. Is that correct?
Yes, Doc.
So this is how the activity series is being used in predicting electrolysis reaction. So number one, if I want to identify a cathode, and that is where the reduction is happening. I'm talking about the the voltaic or the galvanic. That's where the reduction is happening. So basically, you see that the substance that is going to be reduced, that is where we are going to be gaining electron. That's what we mean by reduction. And that happens at the cathode. Now, how do I know that this substance is going to be receiving the electron? When I compare the reactive series or the activity series, there I'm going to see that some of these elements are less reactive than the other. Now, typically the one that is less reactive, like the example that I cited, gold and say potassium. So gold is going to be less reactive. Hence, it has a tendency or the potential to receive the electrons as compared to potassium. Please, is that okay?
Yes, Doc.
Yes, so
Okay. Now, it's the same way if I want to be predicting the anode. The same way it goes like that, that the more reactive becomes the where the oxidation is going to be happening. So we can clearly look at it from that point of view. So this is how we use electrolysis to predict the anode, and of course also predict the cathode. Of course, we can also turn it. We can reverse the what I just said. So we are using the activity series to predict the electrolysis. We can also use electrolysis to predict the activity series, assuming I don't know anything about how this arrangement is made. I can use electrolysis to predict which one will be receiving the electrons and which one will be losing the electron. So for example, I can, if I let me open my paint. Yes. So I can use, okay. Let me put paint. Yeah. Okay. Yeah, so I can use electrolysis to predict. I give example like electrolysis of water. That is breaking down water into its ions. So for example, if I should, where is my marker? Okay. So sorry, let me take a mouse and then use that mouse. Okay. I can't see my this. Yes. Okay, so if I have water, like my mouse shaking. So H2O. H2O when oh, my mouse is not Pardon me, I'm not getting a. Let me use this one. So okay, so H2O, when it breaks down, will be breaking down to form my hydrogen gas, or that of. So if I'm balancing this is going to give me H. So if in terms of that plus 2OH ions. Okay, so basically, if you look at it in the anode section, at the cathode, if I'm talking of the hydrolysis of water at the anode, cathode, this is what is going to happen at the cathode if water is breaking down. So this is the cathode, and then at the anode, if the water is going to be breaking down, at the anode side, this thing keep on vanishing. So at the anode side, then instead of the hydroxide, I'm rather going to create oxygen gas plus my H ion. Okay, so that's H ion. So this is at the anode side. Oh, yes. So in the electrolysis of water, at the reduction side, you're going to see that we're going to be producing hydrogen gas. At the oxidation side, we're going to be producing oxygen gas. Now, if you look at the electrons involved at the cathode side, if you want to balance the reaction, basically what it means is that this side, I don't know why my mouse is getting lost. So at the cathode side, I need to add 2 electrons here. Then at the anode side, I need to add 4 electrons here. Why is my distance not there? Yes, 4 electrons. Oh, let me use let me just use my hand in doing this. So 4 electrons here. Well, if you want to try to balance the equation, that's just that. So we are just looking at it as separate equation. So at the cathode side where reduction is happening, we see that we'll add electrons at the reactant side. Then at the anode side, we add the electrons at the product side. So that's where oxidation happens. And so the basic concept here is that in electrolysis of using electrolysis, basically we can see that since water is involved, and water can go through both oxidation and then reduction. So here we'll see that in this electrolysis case, it's very kind of difficult to tell where is the anode, where that is, we are just using water as both the electrodes, that assuming that the water is in the solid kind of form. So electrolysis of water, when we want to just understand it from the cathode point of view where that reduction is happening, the understanding is that we release hydrogen gas, and then of course that's a reduction. And then if it is at the anode side, we release the oxygen gas. But let's assume that we are just using hydrolysis of, say, sodium chloride. Now, in hydrolysis of sodium chloride, basically what it means is that we are going to be putting the sodium chloride in water. And of course, that you will see that the reduction, which is at the cathode side, the sodium is much reactive than that of hydrogen. If you consider the electrochemical series, let me minimize this. So if we are going to be considering the electrochemical series, we're going to see that sodium is much reactive than hydrogen. Where's my pointer? Okay, so sodium is much reactive than hydrogen. So in terms of hydrolysis of, say, sodium chloride in water, clearly we can use that hydrolysis to predict which one will be the anode and which one will be the cathode. And in this sense, you see that since sodium is much reactive than a hydrogen, then it makes sense that the sodium is the one going to release an electron. So the sodium will be at the anode, whilst the hydrogen or the water will be, or the hydrogen gas will be reduced at the cathode. So that is the sense that it makes here. So if we want to use equation to really balance that, or just write that, so sodium chloride in water. Of course, when water hydrolysis goes through hydrolysis, it's going to break down into this form, either the hydrogen gas at the cathode and then the oxygen gas at the anode, just for water alone. Now we have an addition here. Now this addition will make water to go in one direction. And the addition is that sodium is much reactive than hydrogen. So what it means is that then the sodium is going to be at the anode. So instead of water producing oxygen, which is at the anode, it will rather produce hydrogen gas at the cathode. Is that okay? Please respond. I don't know if I'm...
Come again. It's not okay. It's not that okay. So come again.
Let me go back. So first of all, water alone, when it wants to release electron, it can do both sides. It can go through oxidation. It can go through oxidation. It can go through reduction. Is that okay?
Okay.
And I've given you an equation.
Okay,
here
Doc.
that... Sorry, is somebody asking a question?
Oh no, Doc.
Okay. Then I've given you this scenario that if it is going through reduction, and of course reduction happens at the cathode and oxidation happens at the anode. Now water alone can go through the oxidation and the reduction on its own, which means that water can easily release electron. That's why at the point, if there is any kind of exposure in water, it's quite dangerous, because we don't know which is the electrode which is now attaching itself to. So if you have a naked wire like that, is a naked copper wire, and the copper wire is carrying electrons, then quickly when it falls into water, it's just going to break the water into its form. So it just will make the water go through the reduction. Okay, now the opposite side can also happen, whilst water can also release electrons to another copper. That's where we use water to generate light. So the hydro kind of power. That is that point established? So what it means is that water, when it goes through electrolysis, can break down, as in when it's going through the reduction, it will be releasing hydrogen gas. And when it is going through oxidation, we'll be releasing oxygen gas. And that's the equation which I've written there. Okay. Now we can use electrolysis to predict whether there's incoming, so there's a substance which want to also go through electrolysis. Now that substance can tell us whether, or the water which we use can tell us whether that substance is going to be reduced or that substance is going to be oxidized. And that's what we use. We are saying that we can use electrolysis to predict how these activity series should be like. Okay. Now, in that case, I cite an example like sodium chloride meeting with water. Now, again, note that water itself can go through reduction, can go through oxidation. But when it meets with sodium chloride, what is going to happen is that the sodium chloride is going to break down to sodium and then chlorine, all of them in water. So sodium and chlorine. all of them in water. Is that okay? Now, when it breaks down to such ions, what we should notice that if you take the the activity series, sodium is reactive more than hydrogen. So basically what it means is that then the sodium will be at the anode side because sodium is just going to be the one releasing the electron. That's why we write here so Na plus. So Na plus basically means that sodium releases the electron. Now, if sodium is at the anode side, then the cathode side will be where the hydrogen gas will be released. So the water now becomes or will play the role of becoming the releasing the anode side, which will happen at the cathode side. Well, assuming we have another metal, say for example, silver chloride. So if I have silver chloride, now if I take the activity series, you see that hydrogen is reactive more than the silver. So basically what then is going to happen is that the hydrogen will be at the anode, while the silver will be at the cathode. In that case, the water is going to release oxygen gas, whilst the anode will be at the cathode will be at the silver point. I don't know if I've made some kind of sense here.
Talk is clear. It's okay.
Okay, so basically the key principle here is that the more there are more reactive metals, like I cited sodium, potassium in the, let me go back to that. So if you take the electrochemical series, the more reactive that metal is, then it will not really be reduced in aqueous solution. So what it means is that it's rather the water that is going to be reduced. And when water is reduced, it releases hydrogen gas. Is that point clear?
Yes, Doc.
Yes, Doc.
Now, if it is less reactive metal like copper, silver, mercury, gold, or platinum thereabout, then it means that that will be, if it is just less reactive, then of course it is just going to be at the cathode side. It's just going to be reduced. Now, if it is going to be reduced, then the water is going to be oxidized. So it means that water is going to be releasing hydrogen gas. Clear? Okay. Now, if we take other, so this is just a figure or diagram that if we take other non-metals like oxygen, like the halogens and those stuff, they will be oxidized at the anode. So note that point also clear. The least reactive non-metal like oxygen, the halogens will be oxidizing or will oxidize at the anode. And what it means is that water will be at the cathode. So three things that I've stated now when it comes to the activity series and using that to predict or predicting electrolysis reaction using activity series. I repeat them again. Number one, if we have a more reactive metal, then that will not be reduced in aqueous solution because water is the one that should be reduced instead. Now, when water is reduced, it produces hydrogen gas. That is number one. Number two, a less reactive metal like copper, silver will be reduced at the cathode. Now, when that happens, it means that the water is being oxidized. And when that happens, it reduces or releases oxygen gas. Number three, the least
Please,
reactive
dog, please.
non-metal.
Dog, please.
Hello, Doc.
Sorry, you're asking a question.
Hello, Doc. Look at it. You are going fast. If you can reduce,
Yes, please.
slow
The
it.
copper will be reduced at the cathode and produces oxygen gas.
Okay, I'm stating three things, and just for your information, and that explains the diagram. I'm just skipping all these diagram. Now, the first thing that I'm telling, which I've just explained, is that if we have a more reactive metal, that reactive metal will be oxidized. The water will be reduced. I think that is clear. Now, the product of water being reduced is the hydrogen gas, which we are going to be evolving, which I wrote that equation. That's number one. Number two, if I have a less reactive metal, then it means that that less reactive metal is the one rather going to be reduced, whilst the water is going to be oxidized. Now, when water is oxidized, oxygen gas is evolved. I think the 2 points are clear.
Yes, Doc.
Yes, Doc.
Then I'm adding a third one that says that at least we have not those that I mentioned earlier. If you look at it, those that I've listed here are all metals, comparing those metals to hydrogen. Now, how about the non-metals? Okay, so when we take non-metals, that is the one belonging to the P block. When we take the non-metals, we're going to see that some of them are reactive than the other. Now, I'm talking of the least reactive metals when we compare them. So if I take the hydrogen, where's my cursor? Please, can you see my cursor? Let me change to a color so it's easy to identify. Okay. Yeah, so if I take the hydrogen here, the non-metals that are less reactive will be the oxygen. Okay, so when we are acting with oxygen and of course the halogens, these are less reactive. Otherwise, the others are much reactive than hydrogen. Now, these leads will be will be oxidized. So when you get to have, say, chlorine gas in water, then chlorine gas is going to be oxidized whilst water is going to be reduced. And of course, when I say water is going to be reduced, then it means that we're going to be producing hydrogen gas. I hope that makes sense.
Yes,
Okay.
sir.
So basically, that's just what I'm trying to go through with you. So please note when we are going to be where we can have the oxidation, where we can have the reduction, especially when it deals with water, we can easily release electrons for us to use that electrons. Then which part will be at the anode, which part will be the anode. So the activity series is just a straightforward method which helps us to predict the outcome of electrolysis. It's just straightforward. It can help us to know where reduction is happening and oxidation is happening. That's just the simple way of predicting that. Is that making sense?
Yes, Doc. Yes,
Okay. If that makes sense, then let's try to use this to predict that. So let's predict the product resulting from the electrolysis of 1 molar zinc nitrate at a pH of 7. So meaning it's neutral. So at a pH of 7, let's try to predict um, the electrolysis of such a compound. So what comes into mind? Yes, I'm waiting for your response. So how do we predict the results? If I have a zinc nitrate And of course, if you look at it, it's just going to be in aqueous. And they are giving us a pH condition that is even neutral. So which one goes to what and which one goes to where? Oh, I'm waiting for you. Oh, yes. I show you the activity series again. So is it okay to predict now?
Yes, Doc.
Okay, so let's give the breakdown. So basically, what is
Hello,
going to
Doc.
happen is that
Hello, Doc.
we just need to identify the possible ions that are going to be. Yes, yes, yes. I'm waiting for your concern or question. Oh, I thought somebody wanted to ask something.
Yes, Doc. Can I try? Hello.
Yes, yes.
Yes. Yeah, if you take the zinc nitrate in aqueous solution, since the zinc is above hydrogen, you expect the zinc to, yes, the zinc to be oxidized at the anode, and then the hydrogen will be reduced to liberate hydrogen gas at the cathode.
Sorry, come again. I didn't get you.
Okay, so I was saying that the zinc, the zinc ion that will be found in the aqueous solution will be oxidized at the anode, while the hydrogen will be reduced at cathode to liberate hydrogen gas.
So sorry, my boy disturbed me. So let me get back. So I come again now. I didn't get you. You said the zinc is going to break down to the zinc ion, and then of course the
Yes, so when the
nitrate
zinc
ion.
is, yeah, the zinc, yeah, yes, yes, sir, yes, sir. Uh-huh. And when that happens,
Yes. So,
the
yes.
zinc plus, since it is above hydrogen, will be oxidized at the anode. And then the hydrogen, which form part of the solution, the hydrogen gas, we are going to experience a liberation of hydrogen gas at the cathode after it has been reduced.
Okay.
Yeah.
Yeah. So in terms of that is correct. But then again, we are looking at it again. If, for example, we are not using water, but then the ions that are going to be breaking down, for example, the zinc ion and then the nitrate ion, just using these two, which of these ions will be going to the anode, which of these ions will also be going to the cathode? So in terms of, say, zinc ion in water, then basically we can know that zinc is much reactive than that of the water. So of course, the zinc is the one going to be releasing, whilst the so that will be at the cathode, I mean the anode, and then the hydrogen, I mean the water will be producing hydrogen gas at the I mean the cathode. Is that correct?
At the
Yes,
cathode.
yes, Doc. Yeah.
Yes, Doc.
Yes,
Doc. Mhm.
yes. Now let's take it like we are not having water in the system. It's neutral. So what happens to just the two ions between zinc and then between the nitrates that we have here, or the nitro ion, not nitrates, please, is N2 nitro ions. So what happens to them? Which one is going to go to which in that prediction? So the first part which we did, that is perfectly correct. Now we are also looking at it from a different angle where we are not putting it in water so that the water goes to release the hydrogen gas, but then there's between these two ions. So we identify the ions that we're going to be producing, and the ions are going to be zinc 2 plus, and then the nitro, that's NO2 minus, and that they are all in water molecule, and the pH for that water is just 7. So we are not producing any hydrogen ions. So this question, the pH guides us. A pH of 7, of course, we know that pH is negative log of hydrogen ions. So if we're going to get a pH of, say, 7, means that we are not having, we are in the middle of the concentration, just the middle of it. So we are not kind of involving the water. So what happens is that then the ions which is going to be broken, one will be favored by the anode, and then one will go to the cathode. So in that case, if you write the reaction, let me see if we can. So what I'm trying to say is that we have zinc 2 plus. Okay, these are the ions which we're going to be releasing, and that we have nitro group, which is in this form. Now we are not considering the ion because we said that it's not going to have much concentration, releasing of hydrogen ion, so it's neutral. And so when we look at it, if I should take the zinc 2 plus, take the zinc 2 plus, and that's zinc 2 plus to move to, of course, zinc ion or zinc solid, then what it means is that I need 2 electrons here. Now, if I write such an equation, what does that mean? Is it reduction or oxidation?
Reduction.
So true
Sorry.
reduction.
Reduction.
So
Reduction.
this is reduction.
Reduction.
Yes, doc.
Okay. Now,
Yes.
if you look at it, then basically it will tell you that, well, what we said, if it was only like zinc nitrate or zinc nitro in water, then this would have been oxidation. So the reaction would have changed. But then just taking these 2 ions, then it tells you that this is just going to go through reduction instead of the oxidation. So if reduction, then means that the zinc will be at the cathode, and then the nitro group, if I'm going to be looking at, so NO2 minus, of course, if I'm going to make it more kind of, how do I call it, more positive. So if I'm balancing the equation, then basically this should be, so it should rather be, how do I balance this equation? More hydrogen here, and those, so this is NO3
So, I recommend.
to that of H plus, so that I can put water here. So in this case, the water is going to be at the anode, so that the anode, so this is oxidation. Let me take the whiteboard because this is just, let me use this to, okay, let me clean this and then use this to explain further. So first of all, the pH gives us a different kind of perspective of how this metal is going to be decomposing. And that's the zinc So sorry, the zinc nitro is going to, so we need to identify the ions that are in that. So the ions basically, so zinc nitro, the ions basically will be zinc 2 plus, zinc 2 plus, and then the nitro group. Okay, and this is the nitro group. These are the ions that are involved. Now the question will be, so which one will be at the anode, which one will be at the cathode? Now, first of all, if I should write this at the, in terms of the reaction, basically I'm going to say that the ions, when it breaks down, sorry, the zinc ion, the zinc 2 plus will be reduced. So that is plus 2E, 2E will be reduced to the zinc solid. And such a reaction is just, of course, it's in the aqueous form, but such a reaction is a reduction. And if it is in the reduction, if they are all in the aqueous form, then of course, if that's the case, then water is just going to release hydrogen gas if it deals with this. If this is a reduction and we are just dealing with water, then water is just going to reduce to release hydrogen gas. Okay, and then the OH minus. That is if water is just being reduced. But then we are looking at just this ion. And so there's such a reaction is that. Now, if I take the nitro group, if I take the nitro group, and that's nitro group, once this one is going to be reduced, this is going to be oxidized. So that is just going to give me the nitrate ion, and then we're going to have the H plus. So that is if I'm balancing the equation, I just H plus, and then the electrons will be released, so that I balance the electrons and those. And this is the oxidized form. So in that case, it means that the nitro is going to go to the anode, and then the zinc is going to go to the cathode. Now, just getting one is enough to get the other ion to the opposite side. So if I get to have the ions which are involved, then I can quickly predict that this ion, as compared to the other ion, which is the anions there, then this is going to go to the cathode, as against this is going to go to the anode. Unlike if I have just a metal, so if I have the metal put in water, then the electroactivity series tells me that the metal in that ion is going to be just like metal, which is now in the water, and so it becomes zinc 2 plus, and this is oxidation. And that also tells me that the zinc is going to be at the anode, and of course, because it is in water, the water is going to be releasing the hydrogen gas at the anode. So this will be at the anode. So this is the hydrogen gas plus my OH minus 2OH minus, and this is the reduction. So this will be the cathode, and this will be the anode. Please, did that make sense here?
Yes, sir.
Please, are you there?
Yeah, Doc, yes.
So it's okay.
Doc, for the nitro group. Oh.
So
Doc, the
again,
nitro
you
group,
let me
are we not
take this in.
balancing with water?
Yes, well, if we need a balance equation, then of course we need water here. We need water here.
Okay.
Yeah, so that the
Okay.
equation will be balanced. Eventually, we have to talk about the cell. So if you want to write the cell,
Okay.
then of course we need to write a balance equation. And the cell basically is in two parts, the cathode and then the anode. But the balance equation will tell you which one is the anode, which one is the cathode. Please, does it make sense? So if I want to show you, I want to show you the cell. Let me see if this. Okay, so this will be the overall. If you can see my cursor moving, can you see my cursor?
Yes, sir.
Okay, so this is the overall cell, and the overall cell tells us that if you look at the zinc to the zinc 0, then that is going through reduction. So that is the cathode. And if you look at the nitro to the nitrates, then this is oxidation. And so that is the overall cell. So the anode and then the cathode. So the product for the nitro now becomes the nitrate, and then the product for the zinc ion, which was in aqueous. So of course they are all in aqueous, but this time because the solution was in neutral medium, we couldn't generate electrons from water. But then we are just looking at these ions which are in that water generating electrons. So when we put the overall reactions together, we can get to have the cell of that kind of the overall cell. We can generate that as well. Is that okay?
Yes, Doc.
So this is electrolysis and trying to using activity series in predicting electron. We can also do some calculations here. And so we can talk of the quantitative aspect of the electrolysis. And of course, the quantitative aspect is just a process where we use that in electrochemistry a lot, where there is an electric current which causes a chemical change. Okay, so we through that release of this electrolysis process of this electrolysis, electrons are being released, and these electrons that are being released causes a chemical change in the electrolytes, and of course in that electrolyte it affects the electrode which is in that electrolyte. So we can quantify this movement of these electric currents. And so basically current is just equal to the charge is going to be the current times time. So that's how we can do a simple calculation to just know that. So that's just a theoretical framework or the mathematical approach for this quantifying this electrolysis. Once we know the charge, and then of course we know that the current flowing at a particular time, we can do that calculation. So Q here is the charge, and of course we measure charge in coulombs, and then I is the current, and current is in the amps. And then the T is the time which we measure in seconds. So we can quantify the amount of electricities which are just being generated from the electrolysis. Does it make sense? Of course, how did we arrive at this formula? Then Faraday will come in. So we are looking at the laws of Faraday's for electrolysis. The first law of electrolysis. Sorry, we are looking at the first law of Faraday. That is the first law of electrolysis. Now, Faraday is his name is it Michael Faraday? Yeah, he discovered this relationship between electricity and then these electrolytes which are generating this electricity. So that's phenomenon. He brought that idea, and then of course he expressed various kind of approach, and he calls them the law. the law. So he summarized them into, I think, if I'm not mistakenly, two laws. Sorry, I've gone far. Two laws, sorry, of this Faraday. The first law of electrolysis that states that the amount of a chemical reaction or a change so produced at the electrode during the electrolysis is by a current or just by, so just I'm trying to use the formula to say, to really define that. Let me put my pointer. I'm just trying to use that. So the first law basically is just trying to give us a relationship between the current, which is proportional to the quantity of the charge which is being passed through an electrolytic cell. So there is a current which is going to pass through, which of course will be generating the chemical reaction. But then that current which is passing through, or which is created by electrolysis and is passing through, is proportional to the quantity of the charge which is going through the cell. And the cell, I'm trying to refer to the electrolytic cell here. So that's the first law. And that's mathematically, we represent that as the amount of that current we represent as M. That is the mass of the substance. We weigh that mass of the electrode. We need to get the mass of the electrode out, because that electrode is what is going to release the electrons. And then the Q is the amount of the charges which is passing through. So the first law basically says that once I know the mass of the electrode, it should be equal to a constant times the amount of the current or the charge which is just going to go through. Of course, I've stated here that the current, the charge is related to the current per time. So if I know the current, I can know the charge once I know the time through which it goes through that. And the reverse is also okay. Once I know the charge, I can know the current. So please know the formula. I can give you current and then ask you to find the mass of these electrode. And of course, there's that relation. According to the first law of Faraday, they are related. Are we okay?
Yes,
Yes,
Doc, we are
Doc.
okay.
Okay. So that's the first law. So again, the first law of Faraday basically, if you want to put it in a simple terms, we're talking of the mass of a substance which we are using as the electrode compared to the charge, the amount of the charge which is passing through that electrolytic cell. That's the basic way to state that. Okay, so the constant of proportionality here is just it's just a constant, and that is the electrochemical equivalent. Okay, so basically it's just a constant which we try to define that once we know the mass, and of course we can use standard values to get to have the constant, but we don't have a fixed constant for that. But then it just defines the mass of the substance as compared to 1 coulomb of the charge which is passing through that. So basically Z is just equal to M divided by Q. So grams over coulomb. Please, do we get that?
Yes, sir.
So
Please,
once
Doc, please,
yes.
please go over that one again, please.
So I'm just,
That is it.
can you see my pointer here?
Yes, please.
So the mass of that, the substance, and the substance here is the electrode which we are using in the electrolytic cell. Once I know the mass, that mass is equivalent or is proportional to the charge, the amount of the charge which is passing through the cell. So once I know the mass of this electrode, I should know the charge which is going to be releasing the electron in that cell. And it's proportional, and that proportionality means we introduce constant or proportionality constant. And this is Z. Z basically is just the electrochemical equivalent. And I'm saying that Z, if you want to find Z, is just M divided by Q. Please, you see that?
Yes, please. Thank you, Doc.
Yes, and that. Sorry, come again.
I was saying thank you.
There is air blowing through your this, and I can't really hear you.
Yeah, Doc, he was acknowledging what you said.
Okay,
So he
okay,
said thank you.
okay. Yeah, so basically the Z defines the mass which is being deposited at the electrode on passing through, just passing one coulomb of a charge during the electrolysis. So the unit for Z is just gram per coulomb.
Madam Patience, please unmute yourself.
Okay, so that is the first law of Faraday, and that is what we try to. Now, the second law of Faraday. So that's the first law. The second law, of course, there are examples to try on that, but I'm just taking you through. Then we'll apply the two laws. So the second law has to do with the amount of different substances. Okay, so the first one is just one substance, which is the electrode in electrolyte. So once I know that electrode in that electrolyte, basically I'm going to know how much, and that is proportional to how much of this current is being released. Now, the second law basically deals with the different substances which are going to be used. So that's where we can talk of, say, the anode and the cathode, which are different. Now, the second law of Faraday tried to say that they are also kind of related in the sense that once I know the weight or the masses of these substances, they are just going to be proportional to the masses of these are just going to be proportional to just, of course, the weights. How do I put it? So, well, the substances are going to be releasing electricity or electrons. Now, the amount which they have is equivalent to the quantity of electricity which they are going to be releasing. And of course, the quantity of electricity from the first law is also proportional to their masses. So in ferrances, what it means is that once I know the quantity of electricity, I should be able to know the quantity or the weight equivalent. I mean, it's just more or less like the reverse. In the first case, once I know the mass, I should be able to know the charge, which of course gives you the current. And again, once I also know the current or the charge, I should be able to know the mass. Does it make sense?
Yes,
Doc,
sir.
repeat that part. Repeat that part again, please.
Okay. So the first law, I think that one is clear. Or I should get that first part clear.
The first one
part.
is clear.
Okay. Now the second law also says that there's going to be kind of a different substances.
If I can go back.
Sorry, come
The
again.
first part too. If you can go back to the first part too, before you go to
The first one too. Before we go to the second one.
I should repeat the first one. Okay, let's see. So if I take the first one, Faraday is trying to tell us that once, so I'm going to use an electrode, okay? And of course, that electrode is going to be in an electrolyte, in a solution. Now, Faraday says that once I know that mass of that electrode, I should be able to tell the quantity of electrons that is going to be releasing. Now, the quantity of electrons that is going to be releasing is what we call the current. And of course, current is also related to the charge. So it says that once I know the mass, I should be able to know the charge, the quantity of the charge, which is going to pass through the cell. I hope that makes sense.
Yes, Doc.
Okay, that's the first law. So the first law has to do with just one kind of electrode in in electrolyte. Now the second law says that I'm going to be using more than one electrode. So I have different substances there. Now the second law is trying to say that these different substances, and if I say substance, I mean electrode, will be producing a quantity of electricity, which is going to be passing through that cell. So if I have the electrolytic cell, the different electrode that I have are going to be producing electricity. In other words, they are going to be producing electrons. And these electrons, of course, will move in opposite direction as the charge. So they are related. So it says that this different kind of electrode which I'm going to be using should be by quantity produce the same electricity which is going to pass through the electrolyte. And now, how do I know that it's just going to be the same electricity passing through that electrolyte? The second law says that they should be related to their weight. So once I know the weight of the electrode which I'm going to be using, then I should be able to relate them to the electricity which they are going to be producing. That's a summary of the Faraday's second law. Does it make sense? Please address me so that I can move on.
Yes,
Yeah,
Doc.
Doc, I think it does make sense.
Okay.
It's like, yeah.
Sorry, a minute. Yeah, so let me come back. So basically, the weights of these substances are just going to be equivalent to their kind of electricity which they are going to be producing. So the mass of these substances and that of the equivalent weight, which is the same as the electricity which is passing through, are proportional. So that's a Faraday's kind of a second rule. In that case, if I have two substances and I want to find their kind of relation, then substance one or the electrode one will be releasing electricity one. In other words, equivalent weight. Substance two is also going to be releasing electricity or equivalent weight two. So if I want to find, say, the fraction of how much electricity is going to be released, substance one or the weight of substance one divided by weight of substance two basically is just the same as saying its equivalent weight of one divided by the equivalent weight of two. So the equivalent weight is just almost like that's just proportional to the electricity which is just releasing. So the E here basically represent the equivalent weight of the substance, and the W is just the mass, which is related to the. So basically, like just like the first law. Okay, so this time we are instead of M, we are using W just to represent the mass. Is that okay? Please
Sir,
address and
please.
then we
Sir,
move on.
please. Hello, sir.
Yes, yes.
So supposing you are giving something to work like a calculation, will it going to be in equation, or they will just give you the figures and then you just put it in and you get, maybe you have to solve for
So you
anything.
have to figure out which one is the masses or the equivalent weight. Well, basically in stoichiometry, if you have I mean, if you did the mole concept, equivalent weight, if you look at it, you know that moles is equal to, please help me, is equal to what?
Mass over molar mass or something.
What you are saying reminds me of my mate in GSS. And when you ask her to define photosynthesis, you will not hear anything. Everything will be coming from the nose. I didn't hear you.
You said to find
What is
amount
moves?
of
Just a basic definition. What is moves?
Most is the amount of substance.
Most is the amount of no, I mean the formula.
It's equal to mass over
mass over molar
molar
mass.
mass.
Mass over molar mass. So
Yes.
if
Yes,
I
doc.
say that I want the mass, what will happen?
You make the if you want
Just
the
have
mass,
it.
you
Make
multiply
Mass.
it.
the molar mass
Okay,
by
so
the
yes, and so
By
if
the
I
mole.
want the I mean the equivalent mass has to do with the substance itself. So the substance mass, then basically it's just going to give you the well, let me write it so that we all kind of look at what I mean by equivalent mass. And those are so if we are giving a question, first, if it is the first law, then we are looking at the mass of that substance as against the charge. Okay, so let me take well, let me minimize this and take I will be giving examples, but then so if I'm giving any question, I'm looking at the mass and the charge. This is just a constant, and the constant must be provided. It's just a constant. Is that okay? Now, this charge has also another formula. Is that okay?
Current times what time?
Please, are you okay?
Yes, sir.
Yeah, doctor.
We are here.
Okay. So this constant here, the Z can be the Faraday's constant. It's just a constant. It needs to be provided. We can call it the Faraday's constant, which is approximately that 96 something. So it's just a constant. You don't need to memorize that. But then we can just play with that formula where we have so where is it? Let me clean this on save. Don't save. Okay, so we can just play. So taking the first for law before I come to the second law. So M is equal to, so permits me to say that Z is Faraday's constant, so that it will stack this, and that is equal to that. So the F is just the Faraday's constant, whilst the Q is the charge. Now Q is also equal to I times T. Is that okay? So basically, it means that M is also going to be F I T. Is that correct?
Yes, sir.
Now, moles is also going to give me mass over molar mass. So once I know the molar mass, it means that mass is also going to give me moles times molar mass. So it means that here I can also have moles times the molar mass, which is also equal to FIT. So I can play with this. Okay. Now I can also say that in terms of moles, if I talk of equivalent mass is giving us the molar mass divided by moles. Equivalent mass is giving us mass, I mean the molar mass divided by the moles. And so if I come to the second law, which talks about the equivalent mass, then I can play with this as well. Okay, so the equivalent mass is just that. And of course, I can also play with that. Okay, so that if you are giving, so let me minimize that. So if you are giving that, yeah, so if you are giving this, then we can play with this. So W here is just the mass of the substance, and the E is the equivalent weight. And of course, equivalent weight can be the molar mass divided by the moles. And of course, the moles, we are talking of the number of electrons which are going to be released in such a system. Okay, maybe we should try one or two examples and then see how it goes. Okay, now let's look at this person. We are to calculate the volume of oxygen produced at SCP when a concentrated aqueous solution of sulfuric acid is electrolyzed for 30 minutes during a current of 50 amp. Now, what's the information given there? Can somebody tell us?
Doc, please, the question you are reading is different from the one showing on the screen.
Sorry, this I'm reading a different question. Okay, let's start with this one. I think I was reading a question too, but let's look at this one. Let's calculate the mass of a lead deposited at the cathode during an electrolysis where we have a current of 1.50 amps flowing through a molten lead bromide. That is the electrolyte in 20 minutes. So what's the information we can derive from here? So we have to calculate the mass of that material, the mass of the electrode which we have. Yes, any information from here?
Okay, Doc, I can see that we have current, which is 1.50.
So we have the current, and
Yes,
then we
and then
have
we
what
have the
again?
time.
We have
The time.
We have the time,
Yes, which is
which is 20
20.0
minutes, but
minutes.
then we need to convert that to seconds.
Okay.
Okay. Then what
So,
again can we do?
okay, so with the two, we can calculate for the charge, which is Q is
Yes,
equal to
but
IT.
but we need a mass.
Yes,
so
but
Okay.
to
Doc, there is
calculate
no
the
mass in.
molar mass of the
Okay,
lead
so the molar mass.
bromine, lead 2 bromine.
Please, just 1 minute. I don't 1 minute. Let me settle this boy. Otherwise, you will not understand. Please, 1 minute. So sorry. Okay. Yeah. So the atomic mass of lead is 207. If you check from your periodic table, 207, and then the Faraday's constant here is 96500 coulombs per mole. So this is a constant which needed to be provided. So let me use my pen. So there are some constant which needed. So the atomic mass for lead is 207, and then the Faraday's constant, which in the other case I told you Z, but then I started changing it so that it will stick to you. It's the Faraday's constant, and that is 96500 coulombs per mole. Sorry, coulombs per mole. Please note that. Okay. Now, in terms of trying to address this, of course, the information given here is that we have current, we have time, and we can change the time to seconds. Okay, so the time is in 20 minutes, So how do we change it to seconds? So it's going to give us what?
Multiply by 60.
So 60 seconds make 1 minute. So 20 minutes will be times 6. Is that correct?
Yes,
So
Doc.
60 times 20. Okay. Is that okay? Now we also have current, and the current is 1.5. So the current is 1.5. So basically what it means is that the charge here will be the current times the time. So it will be it's just going to be 1.5 times 60 times 20. Is that correct?
Yes, please.
Yes, Doc. Yes,
Okay,
Yeah.
so
Doc.
that is for the current. Now, how do we address the mass? Well, of course, we need to first of all know the half reaction, so that will tell us the n, that is the number of moles for the electrons, because we will be looking at the the mass. So find the number of moles for the electron. How do we get that? We need to find from the equation what is the number of moles for that. Now, if we write the half reaction, it's lead. So lead going to lead bromide, of course, is written there is lead 2. So the number of electrons will be 2 moles of electrons. And that's 2 moles of electrons. Basically, it's so if you look at the Faraday's constant, the reason why we are using that Faraday's constant is coulombs per mole. So if I should take 96,500 coulombs in every 1 mole, therefore that is the number of electrons which is required to pass through the lead. We need 2 number of electrons to pass through or to be released by the lead. And so the constant there will be changing to the 2 times that of the Faraday's constant, not 1 again, because now it's not it's per column. Now we have 2 electrons in that. And so when we calculate the charge and then we know the constant, then we are looking at the columns which is now going to be depositing in 1 mole of the lead. Therefore, how about the total lead? Let me use that. So the first thing is to write the half equation. Now, when we write the half equation, the reason why we are writing is to know the number of electrons which is going to be passing through the lead, so that we can get the number of moles. Let me say undo this writing. Sorry. Sorry, let me clean this thing first. Erase. So that I use this one. It's interfering with that. Okay. So from the half equation, I know that 2 electrons of this are required to pass through 1 mole. And so basically what it means is that there's going to be, instead of 1 Faraday as a constant, now it becomes 2F. So that's a constant now. My next step is to calculate for my charge, which is just the current times the time, which is 1.5 times 20 times 60. That's the charge. And then I make that conclusion that once I'm talking of mole, moles is mass over the molar mass. Basically, then what it means is that mass is just going to be moles times the molar mass. And so if I know the current which is going to, or the charge which is going to pass through 1 mole of that, which is just equivalent to the molar mass, which is, if I say molar mass, basically is gram over mole. So if I take 207 grams, it's in 1 mole. Okay, so if I convert this, then this is what is going to be happening. So in every 1 mole, which is this, I'm going to be getting a mass of this. I don't know if I'm showing, yes, which is just the mass of this. Please, am I making sense? In other words, I can just find just the mass. Once I know the molar mass, I know the mole, which is S1. How about the mass? Please, am I making sense?
Yes, Doc, we are following.
Okay, so
Hello, Doc.
I'm saying that if I should take this constant, which is the current or the charge which is passing through the lead, and the lead, of course, if I take the molar, basically I'm still talking of moles. Moles is mass over molar mass. And so
Yeah.
molar mass is just like saying that I have a mass in 1 mole. That is what you mean by molar mass. So I'm just doing equivalent relation. So if this current goes through this mass, that is the 1 mole. That's why I converted this to 1 equivalent mole. So if this current goes through 1 mole, when 1 mole is this mass, therefore, how about the calculated charge which I've calculated here? What will be its equivalent? Is that okay?
Okay, sir.
Sir, please come
So,
back again. Sir, please go back
okay,
again. I beg.
let's go back here.
Doc.
Let's go back here.
Doc.
So basically, okay, so I've calculated for a charge, and
Hello,
that
Doc.
charge was that's the Q. Q is equal to it was 1.5 times 20 times 60. Is that correct?
Yes, please.
That's
Okay, and that's, if you punch your calculator, that should give you how many columns? That's
1,800.
yes, 1,800. So 1,800 columns. Is that correct? So this is what we have. Now this column is going to the lead. But you see, if I look at the lead and I take the Faraday's constant, 1 mole of a Faraday's constant is equivalent to 96,500 columns. 1 mole of every equivalent that is equivalent to this. That's a number of electrons which is going to be released. So if I release 1 mole of every electron, then Faraday's constant says that it's going to every 1 mole of a electron being released will carry this particular charge. Okay, now from the lead, I'm now going to see that I'm going to be releasing 2 electrons. So from the lead 2 plus to lead, it means that I need to release 2 electrons to lead. Okay, so basically what it means is that in this particular case, 2 electrons in lead, so 2 moles of electrons, what will be its equivalent kind of a charge which is going to be carried? And that is just going to be 2 times the Faraday's constant, okay, which is equal to the 13, 9. If you have a calculator, that's equivalent to 93,000. Is that correct? Nine 3,000 columns. Are we okay?
So that's correct. Yeah.
Okay. So we have these 2 kind of scenario. So this is in per mole. That is if you are looking at it in per mole. But then this is just the charge. So we want to compare between this and this. Okay, so if 1 mole of this, and we know that mole is basically mass over molar mass, and it's just an equivalent. I mean, we can just do ratio and proportion, but then if that is the case. Now, the molar mass of lead we know to be 207. Is that okay? Is that okay?
Yes, sir. Yes.
So what we need is that we need from between this and this, what will be the moles which is going to be created that we can find a mass. And that's a comparison that I'm just making. So the comparison I'm making here is that between this, if this amount is equivalent in 1 mole, therefore, how about this? This 1,800. Okay, so basically it's just going to be 1,800. 1,800 divided by 193,000. Just to give me the amount of moles which is required for passing through or this current generating. How many moles can this current generated? We know for the 2 moles of electrons in that kind of lead is going to create the 19,300. But we don't know how much moles the 1,800 is going to be creating. So how many moles do we have? So that's why we are just doing this ratio and comparing. So that will be this divided by that. And if you have a calculator, maybe you tell me.
So we get 9.3264 times 10 raised to the power 3.
Okay, where's my one? So 9.3 what?
26.
26
264
times 10 to the power
negative 3.
minus 3 moles. Okay, so now we have the moles. We have the molar mass. So what will be the mass? Mass basically is just moles times the molar mass. So multiply by 207. What will be the answer there?
$1.930.
Okay, so basically that's just a comparison that I was just trying to make. So first of all, the first step is just to write the half equation, and the half equation tells you the number of electrons that we're going to be releasing. And that number of electrons is also helping you to know the constant involved. That's the column or the charge that is involved when it comes to this half reaction. Then the question has given us a charge calculation, which we can calculate to know that. Is that okay? So between the charge of or the electrons released in the half reaction as against that of the charge that we have calculated, how many moles does the one that we have calculated going to be released? Are we okay?
So please, Doc, I want to ask you that anytime you are giving such a question, you have to write an equation for it.
You have to write the half equation so that we know the number of electrons involved.
Okay,
and the number of electrons, which is what is going to create the electricity, and that is proportional to the charge which we are going to be carrying. Okay, where the electrons are flowing, the charge flows opposite of that electrons, and this charge is what creates the current. And of course, Faraday's first law says that the current is proportional to the mass. So that's a calculation we are trying to, that's a basic, what we want to drive home here. So we need the half equation to tell us the number of electrons which are flowing. And opposite that number of electrons is the charge. And that is the current which I've calculated here. And that is the charge. So here it was 2 moles of electrons. Opposite of it was a charge which was flowing. And of course, once we know the Faraday's constant, we can know the charge. Is that okay?
Yes, sir.
Then the question is asking us, okay, in theory, this is what the charge should be. But practically, if I'm releasing a current of 1.5 in 20 minutes, what would then be the mass? So equivalent kind of this thing is in here. So we are now going to find a charge and compare that charge to the theoretical charge which we have. Then we can know the moves and by effect know the mass which is involved. Are we okay? Please, are we okay? Or maybe you should try this question and so that you get.
We're a little bit confused.
Oh, please tell me where you got the confusion from.
But I'm a bit okay, but I think so it's more that clear. But
and so where you got the confusion, at what point did you, so that I can get there and then we all work together?
Yeah. So where you divided the charge by the this and the by the this and the two moves of electron. The charge by
where I divided this one by this one. Okay. You look at this from let's drive it home. Theoretically, you have say 100 CDs. Okay. Now that 100 CDs can buy just say, let me compare to although food is not that this and but let's assume that okay, 10 CDs. Let me reduce. So 10 CD theoretically can buy one ball of a kinky. Is that okay? That is in theory. If you have 10 CD, you can buy one ball of kinky. Now you bought 2 balls of kinky. So how much did you use? Please, I'm making just I'm just making it like a home distance. So basically, what it means is that once I know that I bought 2 balls of kinky, it means that I've used 20 CDs. Is that correct?
Yeah.
Yes, Doc.
Okay. And this is what we calculated here together, 193,000. That is in theory. Now, a reality faces you and says that in reality, you are now having 1.5 balls of kinky. So how much did you use? Can you just guess? So if by theory 1 is to 10, and so 2 will be 20, 1.5 will be what?
15 cities, Prof.
So that how did you get your 15 cities?
Because one is 10 cities, and so half of it will be 5 cities.
So can we say that one ball is just 10 cities? Is that correct?
Yeah.
Okay. So if I have 1.5 balls, then basically what do? I just multiply this 1.5 by 10. And that's how I got my 15 CDs. You agree with me?
Yeah.
Okay. Now I can flip it and say that I use 15 CDs. So how many balls can I buy with my 15 CDs? So basically, this is just a ratio and proportion. It will be 15 divided by 10 times 1. Do you get me?
Yeah.
Now, the question is that we are to produce a current, and of course, the current is given at a time, and that will give you a charge. And this is the charge we have calculated for. This is a reality. This is what we have. Is that okay? Now, in theory, we know that if I take any 1 mole of an electron, opposite of that, meaning in the electrolytic cell, the electrons which is generating the electricity carries, according to Faraday's law, carries 96,500 coulombs of charges. That is in theory. Is that okay? So this particular kind of electrode which we use says that we are not going to be using 1 electron so that we generate 96,500 coulomb, but we are using 2 electrons. So basically, it's just going to give you 2 times that Faraday's constant to know that if I take 2 electrons, which is this question, which is generating this particular 1,800 coulombs, which is these 2 electrons. So then theoretically 2 electrons will basically be 2 times the Faraday's constant, which is this. Is that okay?
Yes, Doc.
Now, the next step is that if you look at it, I'm just expressing this 900 and something, 19,000 or some 993,000 coulombs as 1 mole. It's present in 1 mole. That's this Faraday's constant. The unit is coulombs per mole. So what it means is that it's coulombs in 1 mole. Okay, so this 93,000 coulombs is in 1 mole. Therefore, how about the calculated coulombs that we have calculated? How many moles is it going to be in? Are we okay? Please, does it make sense?
Yeah.
So this is where we then divide. I always tell students, I never understood my teacher telling me if less, more divide, if more, less divide. I didn't understand that thing. All that I need is that which one am I looking for? The one I'm looking for, it should go on top. And the one that I'm not looking for should be divided. So I'm looking for the moles for 1800 divided by the one that is not the one I'm looking for. So that is all. And that I got this number of moles, which is a 9326 times 10 to the power minus 3. Does it make sense?
Yes, right. Yeah.
Okay. So once I know the moles is mass over molar mass, and I was given the molar mass or the atomic mass of lead. So basically, mass is just moles times the molar mass, and I got my mass equivalent. So that's just what I was just trying to compare here. So it's just the same thing. So I got the mass to be 1.93 grams of lead. What it means is that 1.96 grams of lead is what is going to produce a current of 1.5 amps within 20 minutes. Okay, maybe you should try. So this is in mass. Moles can also be in a volume. So we can express moles in various forms. If you remember, moles is equal to mass over molar mass. Moles is just mass over molar mass. It can also be the pressure times volume divided by the gas constant times temperature, if you remember that. It also can be that when we talk about STP, that standard temperature and pressure, moles is basically equal to volume over the molar volume, which is 22.4. Do you remember that?
Yes, Doc.
Okay,
Yes,
so
of
we
course.
can just play. So this is for mass. We can play with volume. So can you try this one if you were following that? Can we try this?
Hmm. Okay. Let's see.
So here we are to find a volume. So at STP, moles is equal to volume over the molar volume. Molar volume is 22.4 dm cube or latest. Okay, so that is given. So once I find my moles, I can find my volume by multiplying it by 22.4.
Hmm.
So how do I find the moles? Is by first writing the half equation. You know the number of electron which is involved. Multiply by that by the Faraday's constant to know the columns. And from this question, you can also calculate another columns which you can make reference and compare them to know the actual moles which will be produced from this current and from within this time. Can we try that?
Okay.
So 2 minutes.
Serious.
I don't think this is confusing, but you try this within 2 minutes or less. Yes, any answer?
Doc, I had 0.0521 dm cube or 52.2 centimeter cube.
52.2
centimeters cube or
you say 0. What?
0.052
Okay. I think
decimeter cube.
approximation. I was having 0.056.
Okay.
But then I think if the understanding is there, let's look at it. So first of all, I write the half equation for that. And of course, it says that the sulfuric acid is going to be electrolyzed. The concentrated sulfuric acid is going to be electrolyzed. And if you look at the electrolysis of sulfuric acid, what it means is that it's in aqueous. So therefore, if you are taking it as electrode and then the anode, then basically the sulfuric acid, the H plus the sulfate ion will go to the reducing part, and then the water will be producing the oxygen. So that is the oxidation part of the water. And so therefore it tells you 4 electrons are going to be released. That's what inference you can make from it being electrolyzed. And so 4 electrons basically will tell you 4 times the Faraday's constant. So that is just that. Now we calculate for the what we are given. The current here is 0.5. The minutes is 30. So we change that to seconds. That will be 900 columns. Now we can compare them and say that between 900 columns, where we have 386,000 columns in one mole. Therefore, how about 900 columns? So it will be 900 divided by 386,000. Then we can get the number of moles. Now that's number of moles times the yeah. So I think you are right. I made a mistake here. So it's oh yes, multiply by 22 times 4. That should give you the 0. I'm not having calculator, but then you can punch it and see. So that's a 0.065 columns in that move.
Say,
Yes.
say,
Yes.
please, my worry is how the sulfuric acid was electrolyzed to have the OH going into the oxygen gas and that of the water. That is my
Okay.
worry.
I think I skipped this. Okay. So basically, when we have aqueous substances in the course of electrolysis, for example, if we are talking of the acid, say for example, sulfuric acid, sodium sulfate, and those things, what we need to know is that they will be going to the anode whilst the water goes to the cathode. Okay, so this is something which is just a general kind of equation which we form from the other kind of ions that we have. So please note these things, this equation. So once we have electrolysis of this, basically you can see, for example, in silver, then silver is just going through the reduction. So that is, so it means that the water will be at the oxidation. Do you get me? So these are some aspect of it which makes the water go through. So if it is at oxidation, then these are the equations which, so when this is in aqueous form, these are the equations that we use. I don't know if making sense. So there's a list of equations when it meets with water, what we are expected to do. So sulfuric acid, when it meets with water, then this is the equation we are expecting. Chlorine, when it meets with water, this is what we are expecting. So at a point, these equations, like for example, lead, when it meets with water in the aqueous form, this is what we are expecting. So we should just note that. So I don't know if this aspect is okay. So I can make progress.
Yeah, doc. I think it's yeah,
So
we get
please,
to see
if you have
that.
a question, can you let me
It's
know
not easy.
quickly? But then, of course,
Yeah.
there are also kind of examples which we can look at that or try with them. Okay, so maybe can we try this? I'm putting this question on my whiteboard. Let me undo this so that at least I make sure that you are okay. So a minute. So look at my whiteboard before we end. Please, let's try this question. Oh, it's not showing. Please, let me use word. It's small, eh? Please,
Yes,
can you see it? It's very small.
it's very small. Yeah.
Let me increase the size and see if uh, it won't work like that. Undo. Let me put again. Bigger size, I can get here. Okay, I can get 40. Right. It's even worse now. No. Okay. Oh, what is this? Wait a minute. Let me do this rather, and then go this way. Okay, then I come to paste. I think it's okay then. Oh,
Yeah.
okay. So it says
Yeah.
that if a current of 3 amps pass through a solution containing silver nitrate. Now this is in aqueous. So that's a equation I show you. Silver nitrate basically will be just giving us just one electron. So if you remember, let me minimize this. So you see that silver nitrate, okay? And that's, it says that it passed through and then within 45 minutes, how much of this silver will be depositing at the cathode? Can we try that? So we are giving the current, we are giving the time which we have to convert to. Please, the atomic mass for silver is 107.9. 107.9. Do I write that, or it's okay? You can get that.
Yeah, we got
Yes,
it.
it's okay.
So 107.9. That is the atomic mass for silver, and then the Faraday's constant is 6,500. Okay, coulombs per mole. Yeah, so 1 minute, can you tell me the answer?
Doc is 9.06 grams.
Is what?
9.06 grams.
9.06
grams.
Okay, that's okay. Please, did somebody get a different answer? So I hope the understanding is coming slow, small. Or still,
Yeah, some
maybe
of us are still
again.
working on it.
You are still
Doc,
working.
please, we are working on it.
Yes,
Please.
yes.
Hey, please be fast. So,
Okay, Doc.
so that's question 1. Question 2. If you finish, try this question 2 for me too. Question 2. Oh, undo. I don't need this. This is also another question. Question 2. Now the atomic mass for zinc is 65.4. 65.4.
Doc, please, the first answer.
I'm not having calculator, so whatever you tell me, and I'm
Okay.
picking this from online, so I don't have answers, but of course it follows the same trend.
Okay,
So
Doc,
what
I
is your
have
answer?
9.056.
Is it different?
I want to ask
The,
Mr. Michael what he has.
Mr. Michael, did you get a different answer?
9.056. So I was approximated it to 3SF, which is
Okay,
9.06.
Okay.
Doc, it's the
So
same
I
thing.
think it's the same thing.
Yes,
So
Doc.
can we
Thank
try the second one?
you. Okay, Doc.
Doc,
And
that
of
is
course, you know,
7.3 grams. 7.3
you
grams.
had what?
7.3 grams.
7.3 grams. Please confirm. I don't have calculator. Please confirm. Hey, oh, you are still working. Oh, okay. So the number of electrons here will be what? For zinc, that will be two electrons, correct?
Yes, 2.
So that would
Yes,
be
Doc.
2 times 96500. And
500.
of course, we need to change the time to seconds. So that would be 1.5 times 60 times 60. Is that correct?
Yes, sir, that's correct.
Okay. So that will be 4 times 1.5 times 60 times 60. And then we'll compare that to 2 times that of the Faraday's constant. Then we get the moles. Now the moles times 65.4. Well, at a point we can play backwards. So you see, we had the moles, and then we multiply by the molar mass to get the mass. Now, how about giving you the moles to calculate for the current or the charge? Please, you get me?
Yeah,
So
yeah, Doc.
yeah, so if I should minimize this, so we can play simply with this thing. So you see this one. Sorry, we calculated for the moves, which is this divided by that to give you the moves before we multiply by this to get the mass. Is that okay? So how about giving you this moves to go and find this charge? Would that be difficult? So we are just
Okay,
reversing it.
okay, Doc, you
Okay.
can work one example with us and then we try the rest.
So I thought you said that give us one example to try. Eh? I was thinking that you said that give us one example to try. So I'm putting one example for you to try. So let me clean this one and then try to see if I can get one example here, which is okay. So that's this one here. So just from copper, of course, copper is also going to give you 2 electrons. So I paste this thing here, and I drag that. So This is it. The molar mass for copper is 63.5. So the molar mass for copper is 63.5. Okay. Now look at the question and then give me a feedback on that. So what is the total charge, of course, required to deposit 0.1 moles of copper in copper sulfate solution? Okay. So what will be the total charge? Q. What is the Q? And of course, we know that if I take copper, so if I should write, if I take copper in copper sulfate solution, then I'm going to be having copper 2 plus 2 electron moving to the copper solid. So basically what it means is that the number of moles will be 2 moles for electron, and that means that I need to multiply by the Faraday's constant, which is going to give me 193,000 coulombs. Is that okay? Okay. Now, once I know this, I need to calculate for a charge. And that was a charge which I was comparing to get the mole. So the moles, which was in equivalent to what I was looking for, was equal to the charge divided by the 193, if you remember the procedure, divided by 19300 coulombs. And of course, now the moles is given as 0.1. Okay, so now the charge is going to give me what? 0.1 times 193,000. 193, so pardon my writing, 193,000 coulombs. Is that okay? Please, is that okay?
Yes, Doc.
Yes.
I can further play with this one and ask you what will be the current when I give you the time. So when I say that, what will be the current in say 20 minutes? So once I know the charge, and the charge is going to give you current times time, and of course the time is 20 minutes, which is 20 times 60. Therefore, this one whole thing divided by 20 times 60, so I can get the current. So I'm just working backward.
Okay.
I'm just working backward.
Okay. Okay.
Is that okay?
Yeah.
Well,
Yes, Doc.
what we are just doing is just the electrolysis. It has applications of the whole thing. And so basically, if we want to look at the applications of these electrolysis, we can be talking about using electrolysis in the extraction of metals. Most of our metals, we use electrolysis to get the pure metals. Of course, we are pushing electrons. So the metals which exist in, for example, in our earth crust, exist as in their compound form, meaning they are in the aqueous form. And so if we push electrons to it, we can release the pure metal like sodium. So once we fetch, say, a seawater, and then the seawater basically contain sodium chloride. And that if you push electrons to that water, we can now isolate there's a sodium metal. So most of these metals which we have, the common way of extracting them is just extraction or maybe refining will just be the usage of these electrolysis. That's one application. Well, so the extraction of copper and those things, these are just a process. Again, we use electrolysis for production of chemicals. So the coastal soda, chlorine gas that we have, potassium permanganate. And of course, for example, potassium permanganate it's so easy to have been producing that. And you know that Ghana Water imports a lot of these potassium permanganate in the treatment of our water. And it's unfortunate that we can't produce them here in Ghana because, of course, we have a lot of manganese being released from the mining sites, especially when they blast these rocks. We have a lot of manganese in Ghana. And potassium permanganate is just, of course, potassium we get in ash. So anything that we burn, like the cocoa ash, so mix the cocoa ash which is potassium hydroxide, mix it with the rocks which we have melted, and push electricity through it. We produce this potassium permanganate. But of course, the cost of the production is much expensive than we going to be importing it, and that's one thing. So we produce some of these like sulfuric acid production, HCl production, all of them we import from outside. So this is just some applications of these electrolysis. So refining, production, and of course using electrolysis as a means of coating materials such as metals. So electroplating and then this electroforming on these surfaces to protect our metals. Well, in that case, then it will lead me to what we call corrosion and how to prevent corrosion. These are common stuff which we did in this level 200. So basically, if we say that corrosion, what is corrosion and what's the difference between corrosion and rust? If you can help me.
No,
Yes.
we know that not all the metals corrode. Some metals
Yes,
rust.
but
Typical
so
example is
what is it?
iron.
So what is it?
Iron rust. So iron rust and other metal like zinc and others, it forms corrosion.
And so what is corrosion and what is rust? You are giving me an example.
So
So what is
corrosion is the
it?
wearing away of the surface of the metal by the action of the moisture and that of the air. That's from my point of view.
So
And the
basically,
rust
can we
is
say that corrosion is the mother and then rust is the son? So
the sun.
corrosion is the bigger common phenomenon which we see in our daily life. And out of that is the rust. So the formation of a layer, for example, in
Bedok.
yes,
The last semester, whilst we were learning it, we know that so the though corrosive is the mother, but we definitely know that corrosion and the rusting are different entities simply because
it's not different.
it's not
That's why I
different.
asked you to define it. So what is
The reason
corrosion?
why the reason I was saying that is
No.
some
So
metals
what is
go.
corrosion? First of all, what is corrosion?
That's what I'm saying. Is the wearing away of the surface of the
So
metal,
what
rather
causes the wearing away of the surfaces?
the action of the moisture and that of the air and other
So
organic
basically, when we
particles.
say corrosion, it's just a process where we want to refine the metal by covering it to make it a metal oxide. Is that okay? And then
Very
rust
well.
is also iron oxide. So corrosion involves rust. But then when we say rust, then we are just restricting it to just some specific metals. But corrosion is basically converting them to their oxides, metal oxides. So corrosion is the bigger picture, whilst rust is a subset of corrosion. Are we okay? Now,
Yeah.
can you tell me some factors that affect corrosion? Yes, I'm waiting for you so that we can end. The time is it's fast spent. So what is the factors or these things you can just find out? I just brought this thing up just because of the electrolysis that we are talking about. So using electrolysis, we can end up with this corrosion. You can see the factors that affect corrosion. You can also see the types of corrosion. That's where you can bring in rust. Then we can see the examples and how we can prevent this corrosion. I mean, can we do that now, or you can read that on your own?
This one we can find them on our own.
Okay,
Yeah,
so
yeah.
that is just that. So that is the introduction to the electrochemistry. Now, I think our next class will be on Friday. Is that correct? Which
Yes.
is five again. So please note that it's Wednesdays and Fridays until we finish, so that we can finish fast. Okay, so now I'm going to take the activity and then we look at it again. So that is just an introduction for the first part. So we'll meet on Friday and then we'll look at other few calculations here on concerning it.
Hello, Doc.
Yes.
Yes, a quick one, if you can address it. Now, from the beginning, you give us a relation where M equals ZQ. M equals ZQ.
And then I said that the Z, change it to F so that it will not confuse you.
So I want to find out that there's a relation between the Z and the F.
We said that the Z is a constant of proportionality.
Yes.
And this constant of proportionality is basically the Faraday's constant. Is that okay?
Is this so confused?
Okay.
Are you okay?
All right. Okay, Doc.
Okay.
He'll be fine.
Oh, please, don't talk for him. Okay, so then we'll see you on Friday then.
Thank you.
Please. So when are you writing? When is the lecture supposed to end so that I know how to manage my time?
Next week.
Okay, so
Doc, this week.
Lectures ends this week.
But no.
You mean this Friday today?
Next week.
Yes.
Next week.
No, it's this
please,
week.
Please,
no, it's next week. Next week.
But
next
doctor said on the next week.
Lectures ends next week, so it means that we can meet Friday and then the following Wednesday and Friday.
Yeah.
Exactly.
So that I know how I can take the whole thing. So it means that today I was very slow. Next time I have to be fast. Because if I have only 1 week, then I have to be fast.
But Doc, the understanding is better than.
Yes, but then I just
need getting the understanding
1 or 2 parts, which is because this is electrochemistry, so we need to really get to have some key electrochemistry parts before the class ends.
Okay, Doc.
We don't have much yet. Yes.
Doc, so some of us, the biology minor students, so the electrochemistry hasn't reflected on our registered
but this thing I thought I don't know, but I don't know if Doreen Bell is part of if she can hear us. I thought we addressed this, why is it? Okay, I'll mention it again if that. So what the problem is that the electrochemistry you registered is not reflecting on your portal.
Previously, it wasn't part of our course. Then we got to know that Dr. Adu informed us that we are supposed to do it. With the chemistry major, every chemistry major student is supposed to do it. So we noted about it and informed the department that they should even bring it to our registered course. Some of the chemistry, because it was appear on the physics minor student portal. But with the biology minor portal, it wasn't part of our courses.
Yes.
So we informed them. But as we are speaking with you, it hasn't even appeared. So we don't know what to do. If we should proceed.
The last time I thought The lady said that it will be taken care of. But let me talk to Dr. Justice and see what is the problem. Okay. So you
Hello,
see
Doc.
on Friday.
Hello, Doc.
Yes, sir.
Hey, Doc, please. So, I think the previous weeks, although I joined the edition, but that time I was having eye problem, so it's like I couldn't enjoy the edition, the lectures that much.
Okay.
So yeah, so there is a question that I want to ask. Like in electrolysis, like
Okay.
let's see if the addition the electrolyte is copper sulfate,
Mm-hmm.
copper sulfate. So in this case, what are the addition the electrodes that I will use for the addition for the
The
electrolysis?
cathode.
So basically the copper sulfate is the electrolyte, is a
Yeah,
solution because that is in the aqueous form. Okay.
yeah,
And the
yeah.
aqueous form basically means that we're going to have the copper 2 plus and then the sulfate 2 minus.
Okay.
Is that okay? And of course, they are in aqueous, meaning they are all in water.
In water. Yeah.
Yeah. So if copper is copper 2 plus and it moved to copper solid, because there's going to be addition of electron, that is going to be reduction. And
Okay.
we know that in the electrochemical cell, the reduction happens at the the reduction happens at the cathode, but then in the electrolytic, reduction happens at the anode.
Yeah. So
Yes.
dog, in this case, the lesson the sulfate, the sulfate, the electrode will be
Yeah. So once this is the anode, then the sulfate will be at the cathode. That
oh,
is if you are dealing with the electrolytic using the electrons to generate electricity. So the sulfate will be at the anode, whilst the copper will be at the anode and the sulfate will be at the cathode.
okay. So dog, the listen the cathode, the listen the electrode, is which material?
Electrode are solid materials,
Okay,
and then the electrolytes are the solutions.
are the solutions. So in this
So
case,
if you
both
say
the listen.
copper sulfate, then copper sulfate is an electrolyte. The
Okay,
solid material which we can use in copper sulfate is the copper.
copper. Only copper.
Yes, only copper.
Okay.
Okay. Okay. Doc, quick one. Oh, quick, please, quick one. Doc, please, can I come in? Quick one.
Yeah, yes.
Yes. I'm getting a little more confused about now. If you express the mass deposit in terms of molar mass, the current, the time, you need to divide by Faraday constant times the number of moles. So you consider the F here is dividing. And so why are they? Is this directly proportional to the Z? That is my concern. Why are they directly proportional? If in the expression, let's say mass deposit is equal to molar mass times current times time all over Fn. So the F here is
Please,
now dividing.
you mean you talking about the first law,
Yes, the first law, exactly.
and you said that why are they what?
Directly proportional. Why is Z proportional to why are they equal?
That that is not proportional to anything. This is it.
Uh-huh.
Z is
Okay.
just a constant, and you see
Okay.
proportionality. Look at
Yeah.
this one. So
Mhm.
it's
Yes,
rather
yes.
the
It's
mass which is proportional to the charge.
okay.
And then proportionality, when if you want to introduce constant,
Yeah.
if you want to introduce equal to in
Uh-huh.
proportionality, you introduce a constant. And that's
Okay.
where the Faraday's constant comes in.
So the Z, you said we can replace the Z with F. Is that
Yes,
correct?
Faraday's constant.
we can replace it with. But I'm saying that this equation we are seeing here can be changed into m times I times t
Yes,
all over
yes,
fn.
please.
Fn. Aha. So if z and f can be interchanged, then that is where my confusion is. So is it that you can express this z rather in terms of f in other way? That is what I want to really get. Yeah.
And I'm saying that the Z here is
Okay.
constant.
Okay.
Okay, Faraday's constant is
Okay.
constant. So we can just interchange. So you see, when I brought the Z here just to tell you it's a proportionality constant.
Okay.
And when we're doing the calculation, I told you that not to could be confusing yourself. Let's
Okay.
represent that proportionality constant with F so that you always
F.
remember that constant is the Faraday's constant.
Okay. All right. That's okay. Thank you.
Okay.
Yeah.
Okay, so see you on Friday. I think there's something which okay, so try to address why your this thing is not on your portal. Okay, I'll do a follow-up and then by Friday this and show.
All right, Doc.
Is that okay?
Yes.
Yes,
Yes.
Doc.
Okay,
Yeah.
thank you.
We are
Thank
very
you
much
today.
grateful.
Have a
Bye-bye.
good night.